So a while back, I picked up one of these Nucleo boards from ST with the goal of turning it into a debug tool for CAN bus applications. One of my goals this year is to learn Rust, so this seemed like just the project to take it for a spin. Now the Rust ecosystem is growing quickly for these STM32 microcontrollers, but there is not a CAN driver available in the HAL crate yet, which means I get to make my own. This is the start of that process. Step 1, and the rest of this video, will be about what I have done so far to get CAN frame transmissions working. Let's first go over the hardware setup here. Here we have the STM32F413 Nucleo board, which is being powered over the USB. For the transceiver, I have a microchip MCP2562 high-speed CAN transceiver wired up on this breadboard. The transceiver is connected essentially like the example schematic from the datasheet. The only differences are I am pulling the voltages right from the Nucleo board, and I am using a 3.3 volt for the VIO instead of the 1.8 volt. I have also tied the standby pin straight to ground instead of controlling it for the microcontroller for now. On the CAN bus side, I have a single 120 ohm termination resistor across the CAN high and low pins, and I have the CAN low side connected to the oscilloscope over here so we can verify that our code is working correctly. So now that the hardware is taken care of, we can start writing the driver. When I'm working on a driver like this, I like to start with the bare minimum code to set up the microcontroller. And what better than a simple Blinky app for that? So here's our basic Blinky application. It initializes the GPIO pin used for Blinky, sets up the clocks using the STM32F4 HAL crate, configures a delay struct that we will use later, and then starts an LED blinking forever. To help with debugging, I added in a very simple logger that can send stuff out of the serial port that's connected to the ST-Link debugger. Now that we have a basic program set up in an LED that blinks, we can start the driver. When I'm working on a driver like this, I'm not concerned about making a nice API, so we just throw everything into main. I'll clean the mess up later after we get an understanding of how the hardware works. The first thing that needs to be set up is the GPIO pins. I'm using the CAN 1 module, so I'll be using GPIO pins D0 and D1. According to the datasheet, these need to be set to alternate function 9 to connect them to the CAN 1 module. These microcontrollers have separate clock enables for most of the peripherals, so the next step is to turn on the clock for the CAN module. For this, we get a reference to the reset and clock control module and enable the CAN 1 clock enable pin. Since the clocks are constrained above, it's necessary to get the RCC module in an unsafe block. With the clock enabled, we can now start to configure the CAN peripheral. Using the same unsafe block style as before, I can grab a reference to the CAN 1 register block. Now the CAN module starts in sleep mode after reset, and I need it to be in initialization mode, so here we set the initialization request bit and clear the sleep bit. The CAN module does not immediately enter initialization mode after it is requested, so now the program waits for the initialization ACK bit to be set. Here's the first example of using that serial logger I talked about earlier so I can track the progress and ensure that it's exiting initialization mode correctly. Now that it's in initialization mode, bit timing can be configured. The bit timing register is configured to set the clocks for 125 kbaud. The clock feeding the CAN peripheral is 50 MHz, and I would like the time quanta to be 500 nanoseconds, so each bit will have 16 time quanta. Each of the fields here are defined as the set value plus 1, so I set the maximum resynchronization jump width to 3 time quanta, the time segment 1 to 9 quanta, and the time segment 2 to 6 time quanta. The BTR register is also where Loopback Mode can be set for testing. Loopback Mode is needed to be able to transmit with only one node on the bus, since it will ignore missing ACKs, and it will also let us test the receive side since all sent data will also be redirected to the receive hardware. This is where things got a bit tricky. Based on this diagram from the datasheet, I assumed that Loopback Mode meant that the physical receive pin did not matter, but that turned out to not be the case. In order to leave initialization mode after clearing the init request bit, the CAN module has to detect 11 consecutive recessive bits on the bus. Since it isn't transmitting anything, that should mean that the receive pin will be in the recessive or high state. However, this diagram is a complete lie, and that is not what happens. It turns out that even in loopback mode, either a transceiver must be connected or the receive pin must be externally pulled up, so a quick addition of a pull-up resistor was able to get the CAN module into run mode. Now that everything is set up and running, it's time to actually send some data. Fortunately, this was straightforward. I write the ID to the ID field, set the data length to 8, write in some data to send out, and start the transmission. With this hooked up to the scope, it is easy to verify that the correct data is being sent. With transmit working, that will be it for this episode. In the next video, we will take a look at being able to receive data and then hopefully start to turn this into a driver with an API that is actually useful. Thanks for watching.